So here, this video is going to cover the basics of rate of reaction, what it is and how we manipulate it. So to start with, it's important to know that chemical reactions are occurring around us all the time. There's a reaction going on inside your bodies right now. In fact, there's lots of them, but one in particular, when you breathe in and out, in and out, that's respiration. So the process of your body releasing energy from the chemical energy within your food. Okay? There's also a reaction happening, maybe if you're watching this video on a laptop or a mobile device, the battery inside that device is converting the chemical energy inside that battery into electricity. Okay, and that chemical reaction is producing electricity. So chemical reactions, there's lots and lots and lots of them that are happening all of the time. Now, some of these reactions are useful and some of them are not. We often wish to speed up advantageous reactions, so the good ones, and we want to slow down unhelpful reactions, the ones that aren't so good. That's why this concept is important in chemistry, so we can use it to our advantage. An example of a good reaction, or a couple of examples, might be the production of medicines. Okay, so making helpful vaccines and things to help those that are sick. And also the manufacturing of plastic. That's a chemical process in which we combine molecules into long polymers to make all of the different kinds of plastics that we use. Okay. The body speeds up reactions involved in the breakdown of food. So that happens naturally, but our bodies have lots of cool things going on, producing chemicals that speed up those reactions so we can get that energy really quickly. Okay. Some bad reactions. Examples include the rusting of metal and the rotting of food. I'll tell you a story. When I was in year 5, I left a banana in my bag for so long that I opened it up and there was all maggots crawling inside. It was the most disgusting thing ever. It was in like a secret pocket that I just wasn't so sure about. Anyway, these kinds of reactions aren't so good and we want to slow them down as much as possible. There are a few ways that we can increase the speed of rate of reaction. Okay, so the speed of a reaction or the rate of reaction, they mean similar things. Okay, so we can increase the speed of reactions by increasing temperature, increasing concentration. That's for liquids, and pressure for gases is the same concept. Increasing the surface area, so that's with a solid reactant, and also by using a catalyst. And I'm going to explain these 4 in this video. The first concept we'll look at is concentration. Now, concentration is a measure of the amount of solute dissolved in a certain volume of water. Now, it could be any solvent, but water is the most common one. So I'm just going to stick with water for this video. The higher the concentration, the more solute particles there are in the same volume of water. An easy way to think of concentration is maybe with something like cordial. So it's quite strong and concentrated in the bottle, and you dilute it by adding water, so the concentration is reduced. Here we've got 2 diagrams. They're not labelled, but I'll explain them. We've got our red solute particles. So in this diagram, we've got 4 of them, and we've got our blue solvent particles. So this picture here is not very concentrated because it's only 4 solute particles compared to 10 solvent particles. But on the right hand side one, there's 3 times as many. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 solute particles and the same number of solvent, the blue ones. So this solution here would be more concentrated than this one, 3 times more concentrated. So what happens in a reaction? So in this kind of image here, we've got a solution of concentration 1m. That stands for molar. So that's just a level of concentration. We won't get into exactly what that means in this video. We've got our chemical reaction here. So we've got a reaction vessel, a conical flask. We've got some marble chips in this flask and some acid. We've got a stopper on the flask. So the gas that's being produced from this reaction is going to go through this tube here, into this beaker of water, and into this measuring device, which is called a burette. Here we've got some notches to say how much volume we're getting here. Now the gas that's being produced is going to displace the water in this burette, so you can measure the amount of gas that's being produced, the volume of gas. This is a kind of a zoom in of what's happening chemically. the reactant particles are coming in. So these blue particles coming in are the acid particles in this beaker. And we've got the grey particles, which are the particles of the solid. That's why they're staying still there. When they collide with enough activation energy, so that's collision theory, you're going to produce products. So one of those products is going to stay in the beaker, and the other one that's coming off is the gas. Now, in order for us to measure rate of reaction, we're measuring how much gas is being produced. So all that's happening here is you've got that CO2 gas coming off. Okay. Here's a graph showing the rate of reaction. So it's the volume of CO2 gas being produced over time. And we've got an increase quite quickly initially because there's more reactant particles. But as they kind of react, you're getting less and less reactant particles, which means the rate of reaction is going to slow right down. Okay? So the graph is going to kind of even out and the slope is going to go more and more horizontal. Okay? But that's our curve that we're getting there for our rate of reaction. Now we have the same concept, but it's a higher concentration, 2 molar, so it's twice as much. If I click play again here, we've got more reactant particles coming in. There's twice as many because it's twice as concentrated. Okay, so that means twice as many solute particles inside the acid, so twice as many collisions with our other reactant. And you can see the effect on the graph. The first curve was down here. Now we're getting more gas being produced more quickly. Okay, so there's an increase in the rate of reaction. Now the rate would be indicated by how steep this slope is, not how high it goes. The height is how much gas is being produced. So the steepness of the slope, so how far kind of how steep it goes, I guess, if you're thinking of walking up a hill on that curve, that's indicative of the rate of reaction. Here's a side-by-side play-by-play. You can see low concentration versus high concentration, twice as many reactant particles coming in for high concentration because we've got more reactant particles. So a high concentration solution contains more dissolved particles than a low concentration solution. So here we've got our side-by-side once again. Therefore, when reactants of high concentration are mixed, there are more reactant particles in the same amount of space, and therefore collisions occur more frequently. So more concentration, more reactant particles equals more collisions. That's the theory behind it. The more frequent the collisions,